Okay, so we're going to look at slopes and tangents and the relationship or the connection, I suppose, between the two of these. And we're going to be going back over a lot of the bits that we've looked at already. So to start off the recap, I suppose, at the top here, we're looking at the idea of differentiation and maybe poking a little bit more in depth about what differentiation means and making sure we're all clear on that. So we use differentiation to find the slope. Okay, we should make the connection here between slope and dy dx. That's what we've been calling the slope. This new dy dx, we called it rate of change, also called the slope in terms of what we're doing. It's generally finding the slope of the line. So for a curve, dy dx is the slope of what we call the tangent. And a tangent has a particular meaning. In maths, you would have done ones when you would have done the coordinate geometry of the circle. A tangent is a line that touches a circle or touches a curve at one point only. So it comes near, it touches it, and it moves on then. So when we look at a curve, say like a quadratic curve like so, oh, lost my screen. There we go. If we look at a quadratic curve like this here, we can see that the slope of the curve changes depending where we're looking on the curve. So if I pick those 3 points there, at those 3 points, if we were to draw those tangents to kind of estimate the slope, we can see that the slopes are fairly different depending on where I am. And we would expect that the curve kind of changes, so the slope is going to be different. And what this means, if we're pulling it all together, is that dy dx gives us the slope of the curve, yes, but the slope of the tangent to the curve. And we can think of those things as the same. So the slope of the tangent to the curve, we're relating that now to this dy dx idea again. Moving on a little bit more, we can find the slope at a particular point by subbing in for x. So if we're asked, what is the slope at a particular point? So like at the previous one, we saw the slope changes. If we want to find it at a particular point, they can give us that point and we can sub in. And lastly, equation of a line. We should remember this from coordinate geometry, but this is our formula for the equation of a line. So let's look at an example, try to pull it all together. So for example, we're going to focus on the function or the graph y is equal to x squared. We should hopefully remember y is equal to x squared is a quadratic graph. Looks like that there. Okay, so we're first of all finding dy dx. We're using our usual differentiation. So if y is equal to x squared, to find dy dx, I multiply by the power. I give my x, I reduce the power by 1. So it's 2x or 2x to the power of 1 if you like. You don't have to put in that 1. The second part says find dy dx at a particular point. So again, we'll just rewrite dy dx is 2x. And let's remember that from what we've been looking at the past few days, dy dx is the slope. We're being asked, what is the slope at the point 3, 4? And this is a good time to kind of look at these coordinate points. And we should remember that any sort of set of coordinates has both an x value and a y value. If we look at our equation for the slope, we only have an x that we can sub into. So that's what we're going to do. So anywhere we see x, we are going to sub in our x value, which is 3, and we are going to get a value of 6. And that value of 6 is the slope of the curve when x is equal to 3. So when x is equal to 3, this value here, so say x is equal to 3, we can say that it's here. If you like, it doesn't really matter. Then what we're saying is that the slope here is equal to 6. The slope of 6 really would be a bit steeper than that one. So looking at those two, that's perfect. Now moving on to the third part, we're asked to find the equation of the tangent. And we need to remember what a tangent is first of all. So a tangent is a line. And to find a line, we need 2 things. We need the slope and we need a point on the line. If we have these 2 things, we can find the equation of the line using that formula that we saw. And that's in our formula and tables book, so we don't have to know it, but we have to just be familiar with it, know when to use it and how to use it. So we need to find the slope, which is obviously one part of it, and then the point, a point on the line, and the point comes in with the x1 and the y1, whereas the slope, we should remember, is your m for a line. So for this line we're looking for, our slope is going to be 6, and the point that we're going to use is the only point they've given us. It's the point 34. And we have to use these two things together because we know that the slope is 6 at the point 34. I've lost the screen again. Count how many times that happens too. So the point 34 and our slope is 6 at that point. So we have to use these two things together. So subbing this in, I suppose, trying to tidy it up a little bit. Y minus y1 is the 4, m is our slope, which is 6, x minus x1, and let's just make this really, really clear. So our slope is 6, our point is the 4 and the 3. Making it really, really clear for ourselves. So y minus 4 is 6x minus 18, and y is equal to 6x minus 14. And that is our answer. That is the equation of the tangent to the curve at this point. So we knew that it had the same slope as what we'd found earlier for the slope at that point, dy dx, and then we used the point itself and our equation of the line to find the equation of the tangent. Looking at the second example, we're going to do exactly the same thing again. So they've given us the equation, or the curve, and they've given us a point. We are asked to find the slope of the tangent. So exactly the same question. Start off by finding dy dx. This is where we test our differentiation skills. 3 multiplied by the 2 becomes 6, the x squared becomes an x, the 4x becomes 4, the 5, the minus 5, when we differentiate it, becomes 0. So we no longer have to worry about that. So that should be 4, not 4x obviously. Now at the point, so at the point 1, 2, so to do this we're going to do the same as before. We are using x coordinate, and we're going to sub that in anywhere that we see x. So we're subbing in a value of 1, and we're adding that together, and we get a slope of 10. And this is our slope. Hence find the equation. So same as before, we use our formula for the equation of a line. We know over here, if we just make note for ourselves, slope and line, our slope is 10, sorry, not line, point. Our slope is 10, our point is 1, 2. So these are my key things for my tangent. So our slope and our point, subbing them in, y minus 2 is equal to 10 on x minus 1. So let's tidy that up a little bit. 10x minus 10, and y is 10x minus 8. Okay, and let's just kind of make that even more explicit for ourselves to see where we've subbed everything in. Yeah, so again, following the exact same steps as the previous question. So once we get the hang of this, we're starting with getting our dy dx. We are then finding that at the particular point. This is only a slight step on now from what we were doing in the previous section. We're now just finding the equation of a line, and this really is just a recap of coordinate geometry, putting all the pieces together, if you like. Now there's one other type of question we could be asked, or one other type of calculation that we might like to do, and it's where we work backwards if we're given the slope. And if we are given the slope, we can use that to find the point on the curve for which the slope will be equal to what we're given, or the slope of the tangent will be equal to what we're given. So when we talk about the slope of the curve, that idea of slope of curve, slope of the tangent to the curve, they're kind of the same idea, because that's where the slope of the curve kind of originates from, I suppose. So we're kind of relating these two things in our head. So if we're given the slope of the tangent to the curve at a particular point, we can use that to work backwards and find out what the point is. So giving us the curve here, and they've told us the slope of the tangent is 4, and we're asked to find coordinates, and we should know if we're asked to find coordinates we are looking for x and y. So we're looking for x and y for this curve at which the slope of the tangent to the curve is 4. So if we're looking at a question like this and we're not sure where to start, I mean we always start by just rewriting our equation or our curve, and we know we're looking for slope, so we make that connection in our head again, slope and dy dx. So let's differentiate, find the derivative. So that becomes 2x plus 2. And we've been told that the slope of the tangent to the curve is 4. So that really means, if we I'll write it up here, slope of the tangent to the curve is 4. And that really means dy dx is equal to 4 where? Or what x? Okay, so we're looking for the x value when dy dx is equal to 4. So let's just make that really, really clear. 2x plus 2 is equal to 4. And then we're just doing some algebra. And we're told that then x is equal to 1. Now, if we go back up to what we were talking about earlier, I said we were looking for coordinates x and y. If we're looking for coordinates, we're looking for x and y. This point, this value x equals to 1, this is on the curve, and we want to know what is the y value that goes with it. And in order to find that, we're going to sub back into the original curve. So to make a note of that for ourselves, to find y, sub back into the curve. And the reason we don't sub back into the dy dx, obviously, is that is the equation for the slope. So that is our general form of the slope of the tangent to this curve at any particular point x. But subbing back into the formula will give us the y value that goes with this x value of 1 for a point that's on the curve. So we sub back in, and I'll do this in red as well just to keep it really clear. So y is equal to, we'll sub in that x value of 1 anywhere we see x, and we follow through 1 plus 2 plus 1, and that is equal to 4. So my coordinates, again just making it really explicit, my coordinates are going to be 1, 4. So those are the coordinates of the point at which the slope of the tangent is 4. And we could work through this question again using that point, and we would still find that the slope is 4 if we were to do it like the previous questions. So the key thing with this section is really trying to really grasp that understanding of dy dx as being the slope, but the slope of the tangent to the curve. And then using that combined with our knowledge of coordinate geometry of the line and the equation of a line in order to find the equation of that tangent. That's pulling all these ideas together. And if you really focus on that understanding, you'll be able to kind of glean this from the questions. But focusing on this idea of dy dx as being the slope of the tangent, knowing that if we're asked to find that at a point that we sub in the x values, not the y values obviously, and then if we're trying to find the equation of the tangent, we're pulling that from our coordinate geometry of the line, from our knowledge from that chapter. We pull that together and we're bringing it all together to find the equation of that